the question says, we want 3-letter words. So we want 3-letter words from the 26 letter alphabet, right? So 26-letter alphabet. And we need at least 1A. 1A in the word. So it turns out like the cases, we can base it off of like how many A's there are. So if we have a 3-letter word, we need at least 1A. So one natural way to do it is to do casework based on how many A's there are. So the first case is if case 1 is if there is exactly 1A. Well, if there's exactly 1A, then we also have the question on where is that 1A? Like the A can be like here, or the A can be in the middle spot, or the A could be in the last spot. So we kind of have like 3 sub cases in this case. But luckily, each of these sub cases isn't too difficult because, for example, for this first case, if we put the A in the first position, then these remaining 2 slots there, they can be any of the other 25 letters. So you would just have 25 times 25 ways to put 2 more letters like at the back. And if the A is in the middle, we can just use the exact same reasoning. Like there's nothing different with putting the A in the front versus the A in the middle. Like the numbers are all going to be still the same, the calculations. Like there's still going to be 25 times 25 ways to fill the other 2 slots. And same with like if the A is in the last spot, then the remaining 2 spots there is 25 times 25 ways. So if we were to add these up, 25 times 25 is 625, then times 3, you would get 1875. And that's our first case, but we have to remember this is not like, we're not exactly done yet. We're pretty close, but like we have more cases to consider because the question says we need to have at least 1A, not exactly 1A. So we have to move on to case 2 when there are 2 A's. So if there are 2 A's, then we can again split it into some sub cases on where the 2 A's can be, right? So you can either have the 2 A's can either be in the first 2 spots, like A, and then something, or the A's can be in the first and third spots, or the A's can be in the second and third spots. So there are kind of like 3 sub cases there. Yeah. So then basically what we would do here is for each of these, we would look at like how many ways can we like put the last digit. So for example, in this case, in the AA and then blank, there are 25 ways for what that last letter can be. Then for in this case, like for the blue part, there are another 25 ways to pick what other letter goes there. And for this green one here, again, there are 25 ways by symmetry. So you'd add these up and you would get 75. So that means there are 75 ways to have exactly 2 A's in the 3-letter word. Yeah. So, and then we have one more case to consider, which is when all 3 letters are going to be A. So case 3 is when you have 3 A's. Well, luckily, this is probably the easiest out of all the cases, because if you want a 3-letter word and all of them are A's, then like you're done. Like there's nothing else to like, you don't have any choices. Like all of them have to be A's. There's exactly one possibility. So after we've counted all our cases, in the first case, we got 1875. In the second case, we got 75. And in the third case, we got 1. So to count how many total ways there are, we would just add up all our cases. So we got 1875 in our first case. We got 75 in our second case. And we got 1 in our last case. So we would have 1951 possible ways in total to count this. And just another note, like we might talk about this later, but there's actually an easier way to solve this question using something called like complementary counting. When a question in combinatorics asks like at least 1A in the word, one like the we're not going to go into like depth on complementary counting right now because our main focus is casework, but just in case you're curious, basically what you could do is there are 26 times 26 times 26 total words in total, like disregarding the condition with at least one A, then we can just subtract off how many of them have no A's at all. And then you would get your answer immediately. So I won't go into depth on how you would do that, but like that's the general idea of complementary counting. But in this case, casework would also work perfectly fine by like carefully breaking up the problem into separate cases and like adding the cases up together at the end.